So today's the last day of class, and what we're going to do today is really just a series of practice problems, okay? These are going to cover kind of the base of coding skills, reasonably the base of coding skills that we expect you to have. Being able to code functions, being able to really express statistical concepts in code, right? What we might not do if we might not have time to do practice problems, kind of mathematical practice problems. In the past, we've done that a lot. If there is time, probably what I'm going to have you do is author binomial problems and author Poisson problems, and then we'll go through them one by one. But we'll kind of push that off to the end. There are certain materials that I'm going to heavily encourage you to review as you prepare for the technical interview. That said, I think a number of you are, most of you are deferring to the next cohort. It turns out that is not going to be a 6-week cohort. It's going to be a 5-week cohort, but we're still going to load extra Python in the front of the class. And we'll probably make a couple supplementary videos, things like that. But yeah, we're still going to slow down the Python portion in the beginning, and increment toward a 6-week version of the course where, we're able to have the fun lectures at the end, including, kind of an intro to machine learning and those lectures that are usually really fun for students and for me too. Okay, so let's talk about the technical interview kind of generally. We'll go over just what the interview is, and then we'll talk expected skills for the interview. At this time, the interview is 45 minutes long. It's timed. So, we book an hour, or you book an hour with us. There might be a little conversation on the front end and back end and whatever, but the actual coding time we constrain to 45 minutes. Is it going to be a hard 45 minutes? Maybe it'll be 45 minutes, 30 seconds, but it's going to be 45 minutes. So what do we do in that space? We ask you to write Python functions that explore statistical or probabilistic concepts. We ask you to solve probability questions, right? Those could be basic probability. Those could be binomial, Poisson, geometric. They could be conditional probability, right? They could be related to simple conditional probability. We're probably not going to ask you on Bayes' theorem at this stage, although leading into August, we're authoring new interviews. And so there's a good chance that we're going to put Bayes problems in there because Bayesian thought and Bayesian approaches are really important. We didn't cover Bayes. We opted to focus on Python instead of the Bayes class this last week. The reasoning being, if you can write Python, you can explore probabilistic concepts, right? That's kind of that's what we see. If you're really solid in Python, you can use the Python to explore math in general. So what kinds of textbook problems, aside from the coding problems? Like I said, problems related to binomial, Poisson, geometric, maybe uniform distribution, okay? Remember discrete uniform and continuous uniform, and potentially Bayes' theorem, like I said. So there are a few things that you're going to want to remember from the general analytic approach. You're going to want to understand sampling, right? Using random choice or using random. That sampling could exist in a number of different ways. Maybe you are sampling a random process and looking at the results, or maybe you're just getting a random sample value, as we saw in the permutations and combinations day. There was a combinations approach where we did a mass amount of sampling, right? If you recall. And, we were able to solve sort of somewhat arbitrarily large combinations problem using that approach. So that's sampling from a phenomenon. You could also sample from, you have a list of stuff, you could sample an item from that list. There's a lot of different ways that we can think about sampling. Now, understanding sampling approaches, you also need to understand, this sort of implies that you understand counting approaches, right? So, you know, if we have binary or trinary, you should be able to write a function that will create an exhaustive list of, you know, binary permutations, or, you know, counting in binary. Binary counting, not permutations, but counting. So, you know, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. If you can do that with code, and that's fairly easy, right? We don't need you to write a decimal to bin converter, but you can write 4-nested for loops, right? That iterate over, you know, 0 and 1, and pack those results into a list. That's something that we've done many times with many different kinds of objects, not just binary, but, you know, trinary or quaternary or ships, right? Or any of these things. Understand counting. Use counting as a basis for understanding how to filter in such a way that you can answer probabilistic questions. You're going to need to be able to code mathematical functions. We're going to do a lot of that today. I think that's one of the easier things, you know, out in the world. You find a function, you code it. In a lot of cases, you know, in many cases, there will be something in there that you're not yet familiar with mathematically, and you need to go look up the symbols and, you know, kind of decrypt it, deconstruct it, watch a few videos. In the real world, we do that all the time, you know. I don't know, if you're interested, I can link you to a presentation I gave on maybe, I don't know when this was, maybe a month and a half ago at a conference, talking about a machine learning model. It's a pretty accessible presentation. The math underneath this specific machine learning model is pretty complex, and it's something that every time I dig into the math, I have to kind of relearn it. And I go and I watch a bunch of videos. I watch the lectures from the person who, one of the people who created this model in the first place, walking through the mathematical foundations of it. And once I do that, I'm like, oh, okay, yeah, I totally get this. And then, of course, I go and present on it, and I don't explain any of the math. I just link people to those videos. That's pretty normal because, you know, if you're a data scientist, you have to understand the math. If you're a client, you don't have to, and that's very normal. But it's not uncommon to, on the fly, go learn stuff that you have not seen before or that you don't know how it works. And you need to learn it to the degree that you need to learn it in order to apply it, right? That's kind of what I'm getting at. So at any rate, I'm gonna have you code some mathematical functions today. It's all things that you've seen already. And if we ask you to code a mathematical function on the technical interview, we're going to provide you with those formulas. We're not going to say, oh, you should have this memorized. I'm a big fan of memorization, honestly, but I don't wish that on anybody. I don't think anybody needs to memorize things. You just need to know where to find it, right? And you need to know how it works. And then one of the big things on the interviews is analysis through dictionaries. So we've been doing that a lot. From the initial moment where we were able to do that in this class, we've been doing that, right? And so can you pack values into a dictionary? Can you check membership in a dictionary, right? Can you take the dictionary values and transform them into other values? Like if you have counts, can you take those counts and transform them into probabilities? Whether it's for a sampling approach or a counting approach. Or if you have probabilities, can you transform those into counts if you have a mathematical formulation, right? These are things that you might need to do. and there's a little bit of math understanding underneath that, but really it's just about simple transforms of dictionaries. And then and just generally this analytic approach, we have a generative process. You take that process, you load the results into a dictionary, and then you interpret the dictionary, you transform, you answer questions, right? Something you're going to need to do that. We're not only going to ask you, hey, code this function. Okay, great, that's it. We're going to say, here, code this function. Okay, we're going to ask you questions where you might apply this function or interpret this function. And that's an important thing to realize. In terms of interpreting results, maybe that looks like recognizing a pattern. Maybe it looks like, and you might think we're jerks for doing this, but I promise we're doing this for good reason. We might introduce a new statistical concept that we didn't teach you, okay? And, it'll rely on your prior code or prior questions. And we might say, okay, I'm going to tell you about this statistical concept, and I need you to interpret it. Interpret this on the fly. And really, these concepts aren't necessarily going to be, they're not going to be out of the scope of your skills, okay? If you got that far in the interview, it's going to be within the scope of your skills. But you're not going to just have an answer, right? You're going to need to think about it and, break the idea down. And we'll give you clues, right? We'll point you in the right direction. Usually at that point in the interview, if you're at that point in the interview, it's likely that you don't need to get this right, okay? Unless you've struggled quite a bit before. But we do need you to be able to understand it with help, okay? So that sounds a little vague. When you're in the interview, you'll see exactly what I mean. It's either that, or you could go study every statistical concept out there, every formula, whatever, and hope for the best, right? And you'll probably come across a lot of the things, the things that we might throw at you. Okay. So with all that, let's practice, and we're going to practice functions that we've already seen. Okay. These are all pulled from the slides, and I kind of just did this, and I might I did this in the last 20 minutes. It occurred to me, like, hey, this is a thing that we can do today. Usually I invent a new technical interview on the spot for this class, and as a result, I have a bunch of technical interviews floating around that are of varying quality that we don't deliver as technical interviews, but I do hand them off as platforms for review. But I think for us, it makes more sense to focus on the functions that we've already written, the problems we've already looked at, and because of that, we're gonna kind of do this. So first, code the mean function, and I gave you a list. Instead of 4 minutes, let's do 3 minutes. It'll probably take me at least a minute to find the actual file that I'm working with. So go ahead and get started on that. Okay, yeah. So I'll go ahead and code through a solution for this. So that this trim parameter, optional, right? As it says, it's just a bonus. This is one of those functions that just off the cuff, I think, should be able to code. If you find this function to be difficult, let me know, and I can give you other challenges. Just get in touch with me on Slack, and I can provide you with some other practice problems. Okay, so here's our test list A, and this is going to be called mean. I'm going to pass in a list, so def mean. I'll make this a little bigger. Def mean, and it's going to be a list, and I have a trim parameter that I'm going to set to 0 by default, and because if I'm using the trim parameter, I'm going to make a copy of the original list. Okay, so let's say list gets list.copy, and if trim by is greater than 0, then here's an interesting thing. We could potentially just say if trim by, okay, because 0 is false, 1 is true. So I'm just gonna go ahead and do that. Although if somebody puts a negative number in there, the function's gonna break. But let's not worry about that. Let's just assume this is gonna be fine. And we're gonna get the sorted version of the list, and we're gonna go from trim up into negative trim. Okay, so that's gonna take off the first and last if trim is set to 1, or the first 2 and the last 2 if trim is set to 2. And then we can just return, well, what is the mean? The mean is the sum of items divided by the length of, or the number of items. So it's just going to be that. Sum of the list divided by the length of the list. So let me just make sure that is working. And we'll pass in A, and we'll set trim to 1. And I think, yeah, that's convenient. That's already in order, so we don't need to verify that. Okay, so what is this called? Python TI prep. Trim by is not defined because I called it trim. And there we go. Should probably print this. 47.5. That seems reasonable, between 5 and 220. 47.5, 220 is dragging it out to the right. If we trim by 2, I think it's going to be more representative of the more middle value. So something around 26. That seems more reasonable. Although 67 does stretch this to the right as well. So maybe we'd even trim by 3 if we cared to. If we're looking for something representative and we think that these numbers off to the right are extremes. Okay. So that's our mean function. The next function I'm going to have you write is the median function. Okay, and this one's more involved, right? You have to think about this more. This says 6 minutes. I'm going to keep it at 6 minutes. I think often people struggle a little bit to code the median function. Do your best on it. This is one of those ones that if you struggle with it, look at it every day. Try to code it from scratch every day, because the median function represents a family of patterns that, honestly, it's one of the best representatives for a whole bunch of other types of functions you'll write in the future. So yeah, go ahead and get started on that. And I'm putting 6 minutes on the clock. If you didn't get to a solution on this, don't worry. Don't worry. Like I said, this is not the easiest function in the world. Okay, I'll just say it like that. So I'll go ahead and code through a solution. And this will be def median. We're just calling it median. Make that a little bigger again. And we're just going to pass in a list. So we're going to sort the list first, and I can just use the sorted function to do that. And there are going to be two cases, right? The list is either odd or it's even. And I'm going to start with if the length of the list mod 2. That means that it's odd. That'll equal 1, right? I could put the equals 1 here. I don't need to. This is just checking to see if it's odd. So the middle value is going to be the length of the list divided by 2. Of course, this needs to be an integer because I'm going to use it as an index. And then I can return list sorted sub mid. The reason it's that easy is that, there's an equal number of items on either side, and then there's this one item in the middle that is our median. And otherwise, it's a little more complex, but we'll handle the even length list now. So there's the upper middle index, and that's going to be this value that we see up here for mid, this same operation. That's going to give us the median, the value on top of the median, and then we can use this to get the value below the median, right? This is upper middle index. The value right below that is the upper middle index minus 1, okay? So we can just, at this point, return the, let's look at the two values, okay? So list sorted, we've got the upper middle index minus 1, right? That's our lower value. And I'm going to just pack this into a list with the other upper value. So list sorted, and I'm going to do upper middle index. Oh my gosh. Thank you, code completion in VS Code, for making my life easier. Okay. There we go. All right. So I've got those two values in a list, and I can just return the mean of those if I have the mean available. Otherwise, I'm going to sum them and divide by 2. Either way is totally fine. Okay. Oh, sorry. I think I should put these. Sorry, I should put these solutions in the Slack as well as we're going. So I'm going to paste in the mean first, and then I'll paste in the median. Okay. So the next one we're going to look at is the variance function. Okay. And variance is going to rely on the mean, right? So you're going to call out to the mean to get, sorry, one sec. There we go. All right. So we've got two different forms of the variance function, right? We've got the population variance and we've got the sample variance. And the difference between those is, not huge. It's just we either multiply our summation by 1 over n, the number of items, or we multiply our summation by 1 over n minus 1 for the sample. Okay, so let's do 5 minutes on this. I think I have 4 minutes on the slide, but let's do 5. Right? Whenever you see this summation, this weird looking e right here, that means you're likely going to use a for loop, right? You're going to loop through these things. And just to describe this, this is each item in a list minus the mean, right? Squared. All of those get summed, and then they get multiplied by 1 over n or 1 over n minus 1. So I'm going to go ahead and start a timer for 5 minutes. And yeah, do your best. Okay, so let's code through this. I'm just gonna grab these. Oh, I can. Okay, apparently I can't take a screenshot of a screenshot, so that's fine. I'll just make this tiny and put it up here. Okay. It occurred to me I did not test this median function. Let me just make sure it's not horribly broken in some way so that in case anybody is going to use it. Okay, good. And does that look like the median? It does. Great. Perfect. Okay. So coding the variance function. This, this is a little more involved. This is a number of lines of code if you're going to include Bessel's correction. So let's go ahead and just run through this. So name is variance. We're going to pass in a list. And then I have this flag. We're going to assume it's a sample, but we're going to account for the condition where it's not a sample. Okay? And then we'll say the mean is going to be the mean from a list. And then I'm going to just make an accumulator. Okay? Maybe I'll make that a little bit smaller, if that's okay. Okay. So for each item in the list, I can increase this total, right? I can just accumulate into the total the item minus the mean. We have the mean defined, right, already above on line 299. And then we need to square that. At the end of this, I'm going to say, well, if it's a sample, then we can return the total divided by the length of the list minus 1. And otherwise, we can return the total divided by the length of the list. I can make this a little bit simpler. I can get rid of this condition entirely, and I think this is nice. We can just say 1 minus length of the list minus sample. If sample's true, that's going to be the length of the list minus 1. If sample is false, length of the list minus 0, right? So that handles our logic a little cleaner in that instance. So that is a solution. Well, let's make sure it's not broken in some way. I'll just go ahead and run it. And that looks like a reasonable variance to me. So let me just double check. Oh, yeah. That definitely looks like a reasonable variance. Now, why is it so huge and weird, uninterpretable? It's because it is a square, right? It is an area, as opposed to the square root of that, which would be our standard deviation. Speaking of which, I'm going to have you just code the standard deviation function really quick. And this shouldn't take long. I just put 2 minutes on for this. We have these scary looking formulas, but if you think about what this is doing, you should be able to code this up in no time at all. Okay, so I'm going to put 2 minutes on and go ahead and code the standard deviation function. Okay, so let's go ahead and work through this. All right, so standard deviation is just the square root of the variance, and we can write this pretty easily by, well, I can say from math, import square root, because maybe I'll use that later. Although you can just exponentiate to the 1/2, which is completely fine. Okay, so standard deviation, list, sample, let's assume it is a sample, and then I can return the square root of the variance of the list, and I'm going to pass in sample. So let's see what that looks like in relation to the variance. And remember, A up here, which is all the way back here, we've got these values out to the right, which are going to stretch the standard deviation. If we were to trim those out into something a little bit neater, you know, I think we could see, we could interpret the standard deviation a little bit nicely, a little bit nicer. 622.46. That sounds very reasonable, and maybe I'll do a B here just to kind of demonstrate what I mean. So list of the range, and let's do from I don't know 0 to 25, and let's pass in B and work on interpreting that, right? So the average distance between each data point and the mean is around 7.3. And if we think about the mean, well, we can just say print mean of B, and we can start getting an idea of how to interpret this. Okay, from 12, on average, we're going to go up 7, we're going to go down 7, and that makes sense if we're talking about the average squared distance between, or you know, the average distance between each data point and the mean. It looks like it should be around 7, right? Hope that makes sense. That's a way to think about standard deviation. And yeah. So let's continue forward. Let's see, yeah. Let's code a classic that I think all of you should know, should have coded like too many times already. So go ahead and code Factorial. I'm going to put 3 minutes on. Okay, so this is one of the classics. We'll say factorial. And I'll say factorial of n. And product, right? We're doing a multiplicative accumulation here. And I'm going to say for num in range, I'm going to go from 2. Doesn't really matter, but I'm going to go from 2. Could go from 1. That'd be fine. Product times gets n num, and we can return the product. So if I test this, this will be factorial, let's say of 5. This should be 120. Oh, num reference before assignment. Oh, that's why. 120. Cool. So let's build on this. Oops, left that up there. And I'm going to have you code another quick function, the Permutations function. So here's the formula for that. And sorry, I should really be. Let me make sure I'm pasting everything in as we go. The last thing I pasted in was median, so I should paste in variance as well. Okay. There's variance, standard deviation, and factorial. All right. Oops. Okay. So I'm going to have you code the permutations function. Recall that permutations, we can think about that as arrangements. If we do 5 permute 5, that should just be the same as factorial of 5, right? Because it's the different ways that we can arrange 5 objects. Although we could take 5 objects and arrange 3 of them, right? So 5 permute 3. That's another, another kind of question we can answer with permutations. So I'll put 3 minutes on and go ahead and code that up. Okay, so let's code this up. All right, so we've got permutations, and that's n permute k, and we can just return the factorial of n over the factorial of n minus k. So we can just translate that pretty directly. I like to cast this as an integer. I think it makes sense. And I'm going to print permutations of, let's do 5 permute 5, and then let's do 5 permute 3. And yeah, let's see what those are. 120, ooh. That's why. Okay. Factorial of n minus k, not 0 minus k. Okay, that makes sense, right? We've reduced the space by 2, and we ended up having it. Okay, so let's go a little bit further. Oh, you know what? Let's take a 6-minute break, and when we come back, we're going to jump right back into it. Not everything is going to be coding problems. The next one is not a coding problem, but yeah, we'll see. Okay, so I'll put 6 minutes on the timer, and I'll see you all back here shortly. gosh. Sorry for that. Okay, let's jump back into it. Let's see. So just did permutations, and so we should think about the kind of problem, the kind of question you might answer with this permutations formula. So I'm going to have you write a permutation story problem. I'm going to put 4 minutes on for this. And short story problem, doesn't have to be elaborate. You know, write it and provide the answer to it. So I'm going to put 4 minutes on for this. And yeah, go ahead, do that. When you get to it, just drop it right in the Slack. Okay, So, awesome. Let's look at both of these. Okay. Oh, whoops. Okay. All right. So Paul has 7 cats. He cannot tell them apart, so he numbered their tags 1 through 7. Paul wants to know how many different ways his cats can come inside if they come in pairs, one after the other. Paul knows statistics, so now he knows there are only 42 different permutations his 7 cats could be entering in pairs. Either 1, then 2, or 2, then 1, or 1, then 3, or 3, then 1. If they're coming in pairs. Interesting. Okay. Oh, okay. So this is a question on. I see. The cats will always be entering in pairs. That totally makes sense. Yeah, this is totally a 7 permute too. Awesome. Perfect. And if you have a 6-sided die, how many arrangements of rolls with 1, 2, and 3 pips can there be? The arrangements of rolls. Oops. I'm not sure if I'm understanding the question. Is this... Oh, and that's fine. Don't even worry. It's interesting. It's sort of like the revert. How do I say this? It's a really good learning pattern to invent a story that is like another story, right? And permutations problems are like this. Combinations, binomial, Poisson, geometric, Bayes problems. They're all sort of like this, where you can do a bunch of these problems and practice them up and practice. And if, let's say you do that, of course that's going to benefit you. And what benefits you even more, or by leaps and bounds, is you write a new problem. Every problem you do, you write a new problem based on it. So the way I would go about that with this prior problem is, I don't know, Leon has a set of, I don't know, we could say 8 plumbing tools. He never needs more than 2 of them at a time. Okay. One for his left hand, one for his right. I don't know, something like that. And then we can ask the question, how many different ways can Leon hold any 2 tools in his hands? And the hard part about these is that, okay, when you read these in the first place, you have to figure out what's being asked, right? You have to look at that in the real world and bring it back into the abstract world. And that's not easy, right? That's hard. And it's also hard to invent these kind of from nothing. But it's important to get into the habit of asking questions, right? Asking certain kinds of questions. Now, if it didn't matter which tool was in his left or right hand, it would be a combinations problem, right? But like, let's say a wrench in the left hand and a, I don't know, pipe fitter in the right, or, like, that is specific. And if we switch those around, then order does matter. So this would just be 8 permute 2 in this instance. But if it's hard to write these, if it's hard to do this, that's okay. Find more problems, right? Find more problems with worked solutions and mimic those problems. Just change the story so it still makes sense in light of the probabilistic phenomenon. Cool. Okay, so the next breakout, back to coding, you're going to code the combinations function. And let's just do 3 minutes for that. And yeah, I'll set the timer and go ahead and get started. All right, so this is, very similar to the permutations function. We just reduce the space further because order doesn't matter. So I'll write this in the simple form, def combinations, n choose k, and we can just return the factorial of n divided by the factorial of n minus k multiplied by the factorial of k. And that should be it. So, let's print combinations of 5 choose, let's do 5 choose 3. And just make sure that this isn't broken in any way. 10, okay. That sounds right to me. All right. Oh, keep forgetting to do this. Sorry. Did I put permutations in before? I think we all have permutations, right? Okay, I need to put permutations and combinations. Okay, so that, I think that, you know, definitely on your own time, write a combinations problem. You know, something that sounds like the real world. And you know, when you practice these, again, try to write a new problem based on your practice problems. So we're going to get into the distributions again. And this is going to be a series of breakouts. And we'll take these one by one. I did not include all the breakouts. I sort of chose between closed formula and a little bit of sampling. So, and I should say this, I'm not expecting us to get through this whole slide deck. I put this together so there's sort of a one-stop shop for like all the things that we might expect you to be able to code offhand. But it's not exhaustive. And unfortunately, I can't give you an exhaustive list of like, this is what you're going to need to code. But you could, anything that you've coded in here so far is something that you might need to code on the technical interview. So I want to be clear about that. But yeah, so you're going to code the Bernoulli function. And this is just going to return a 0 or 1 based on the results of a call to random from the random library. So I'll put 4 minutes on and go ahead and code that up. Okay, so this one's a little tricky, and one of the things that we'll need from this is we'll need random. So I'm going to say from random import random, and I'm putting that at the top of the file. When you see this, hopefully it won't feel too complicated. It's simple, but it's tricky. So we've got Bernoulli, and we have the probability of success. And I should get rid of that up there. Okay. By default, let's assume this is 0.5, but it won't really affect anything aside from the probability of getting a 1 or a 0. So draw is going to get a random, is going to get a random number between 0 and 1. That's what this random function does. And then if the draw is less than the probability of success, we can return 1, which means it's a success. And otherwise, we can return 0. I don't need to put an else here. I usually don't when I'm in my own code, but that's, that will work. So let's call this, just make sure everything works in a sensible way. And let's set the probability of success to 0.2 and run this a few times. And we should see that it's fairly, we're going to get a lot of zeros, but we are going to get a 1 in here eventually. There we go. There's a 1. And really we should get something like 2 out of 10 ones on average. So that's Bernoulli. I'm going to have you code a different function that is not dependent on Bernoulli. Okay, just to be clear, we're not going to depend on Bernoulli for this. We are, if we get there, if we get far enough, we will use Bernoulli later. But we're going to write a different kind of function that takes where you're going to need a different function from the random library. Okay, so you're going to code a function called getListOfBits, and it should take one argument, the number of bits, and it should return a list that contains random 1s and 0s. Okay, so I'm going to put 4 minutes on the clock for that, and yeah, do your best. All right, so let's go ahead and code this out. We'll also need the choice function here, so I'll just put that at the top. I'm going to, what are we calling this? Get list of bits. So def get list of bits, and has one parameter, which is the number of bits. So n bits, and then I'm going to do this. I'm going to write a comprehension, but I could do this long form, but I'm just going to write a comprehension. So choice between 0 and 1 for whatever in range n, and that should work. So let's print this. Let's set the number of bits to 8 and find out if that works. N is not defined. That makes sense. N bits. And it looks like that works. We get a random list of binary. Okay. Okay. So this next function is getting into dictionaries, and let's take 5 minutes on this. I think that'll be good. You're going to write a function called binary. I don't know what's going on there. Binary sampling dictionary that has 2 parameters: the number of bits and the number of samples. And you're going to return a dictionary where the keys represent the number of successes and the values associated with those keys represent the count of that number of successes occurring. So if you sample 1,000 times and, you know, out of 1,000 times, maybe you get 35 times where there are no ones in an 8-bit list. Maybe that happens. Does that sound right? I don't know if that sounds right to me, but you know, in terms of the count of bits. So your dictionary should have some structure like this, right? Where the key is the number of bits and the value is the count of that number of bits occurring. Okay, so I'll set a 5-minute timer and go for it. All right, so let's go ahead and code this. I'm just going to close that. All right. So binary sampling dictionary. We're going to set the number of bits. We'll set that to 8 by default, and we'll assume 1,000 samples by default. Okay, so we've got a dictionary. Oops. And we're going to say for whatever in range the number of samples. The binary that we get out of this is going to be from here, from get list of bits. Okay. Get list of bits, and this is called num bits in conflict with n bits up there, but whatever. It'll still work. There's going to be some sum, right? I'm going to call it k, is going to be the sum of binary. And here's where we check for membership in that dictionary. So if k is not in the dictionary, then d sub k is going to get 0. And in all cases, d sub k is going to get incremented by 1. So we can return that dictionary. To traverse this for key value in, and I'm just going to call this directly in that, let's print an f string of the key and the value, k and v, and then cannot unpack non-iterable object. That is my favorite error. It means that I forgot the .items function, or method, that is. Okay, and what we get out of this is a distribution of counts. Notice it is in no particular order. It's going to be helpful for me to wrap this in the sorted function so that I can interpret this a little bit easier. Okay, and if I run this over and over again, of course, we're going to get different counts for these different things. You know, keep in mind that you can run this a bunch of times, right, and average the results. That's something you can do, and that will get you closer to the theoretical distribution of counts. And if you want to see probabilities here, that's easy enough to do. You could just say this is, you know, v divided by the sum of all the values in this dictionary. In this case, we could just assume 1,000. Because this should sum to 1,000 no matter what. So that count divided by 1,000, that should give us our probabilities. And it looks like it does, okay? So let me comment that out. I think we've got time for one more. Yeah, at least maybe 2 more. And let's just go ahead. Oh, do we not need to do d sub k gets 1 if not in the list? Good question. Okay, this is a really good question. So this is my code style right here. I could set this to 1 instead. I could say this is 1. And then I would have to do an else here, if that makes sense. So if k not in d, then d sub k gets 1, and then we skip to the next iteration of the loop. Otherwise, we can say, you know, else d sub k plus gets 1. This logically is results in the same thing as doing this. Doing this. In this case, I'm initializing d sub k to 0, and then I'm just incrementing it every time, no matter what. Exactly. Yes. Yeah. So either way is fine. I personally prefer this way. It's more how I think. But you're more likely to see it the other way, to be quite honest. You know, you're more likely to see an if else. But they ultimately are the same thing. I don't see one as being computationally, I don't think one is better than the other either. I think they're equivalent. Okay, so the next thing, I'm going to have you code the binomial PMF. You've got your formula here. It's got 3 parameters to the function itself. N, which is the number of trials, P, the probability of success on any given trial, and K, the number of successes that you want to find, for which you want to find the probability. Cool. So 3 minutes. This is just committing, committing the function. And recall that this is a n choose k. That's what that is right there. That n over k is n choose k. So that's combinations right there. Okay, this one pretty straightforward. It's just writing the function. So I'll write that really quick. This is the binomial PMF, n, k, and by default we'll do 0.5. And then we're returning combinations of n choose k multiplied by p to the k multiplied by 1 minus p to the n minus k. And then let's do, well, I don't know. Let's do something that looks like the prior problem. So n is 8, k is 4, and p of 0.5. We'll keep it at that. And this should kind of align with that prior problem. 0.27343. And here we're seeing 0.293. Reasonably the same. Remember that this up here was from a random sampling process, not from the closed formula. So of course we're not going to get the same exact answer, but we're getting close. So just a little verification. And let's do one more. Yeah, let's do one more. And we'll do 4 minutes on this, and then we'll, I'll just answer questions from then on about the interview, about what I can answer regarding the DSI, and we'll call it a day after that. And I'll stay on to answer questions at least for a few minutes. I do have an interview, a technical interview that I'm conducting not long after our end time for class. Okay, so you're going to code the binomial CDF, and we've got the formula for that here. This is accumulator pattern, and it's going to rely on the prior function, which I should put in the Slack because I did not do that. So go ahead and code that up. And I'll put 4 minutes on the timer. Okay, so that summation symbol, that big E that you're seeing there, that is just indicative of an accumulator pattern, right? So we're going to sum a bunch of stuff up. It'll be pretty straightforward. It's just going to depend on the prior function. So we're calling this binomial CDF. N will do, I'll call this K high, and then 0.5 as the default probability. And this is our accumulation. And I can say for K in range, we're going to look at the probability of 0 successes up to and including K high. And then we just increment this. Binomial PMF and K and P, which we have. K is coming from within the for loop. And we can return cumulative, and that looks like it should be pretty good. So let's look at this in relation to the prior couple problems. Let's say N is 8, K high is 4, right? So 4 is our expectation, and we'll leave the probability at 0.5. So this should be above a 0.5 probability. It's 0.636. That makes sense. If we were to do, let's say we did 9 here, and see what we get. We get 0.5. That shouldn't be too surprising, right? Because that's going to be 0 through 4. That's 1/2 the distribution. And this is a symmetrical distribution because it's got a 0.5 probability. And then 5 through 9 should be the right half of the distribution. So we can see that very clearly right there. So, okay. So, wow. I thought we'd have a couple more minutes before lecture ended. I'm going to go ahead and stop recording, and feel free